right, so we're going to continue with some particular theorems about tangents, in particular of a circle. So there are a few theorems that I want to look at with you today. I'm starting at the first page of your handout for 10.1, and this is the bottom of the first page. So this says theorem 10.1, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Now, I didn't talk about this point of tangency in the first video, so I'm going to talk about that now. So what this looks like, and I'm going to draw a diagram over here to the right, and it's a little complicated, this diagram. So I'm going to have a circle here, and I'm going to put D as my center, and I'm going to draw the radius BD. So I'm going to call this B. And remember, if it's a tangent, it's a line, and it touches the circle at one spot. So that one spot, that one point, the point is the point of tangency. So now I'm going to come through here, and I'm going to draw my tangent. So this is going to be A, and this is going to be point B. So I have point A and point B. And now what is new is that we are saying that this radius is perpendicular to that tangent. And so I'm going to write that out symbolically. So if line AC is tangent to circle D, then line, oops, that's supposed to be a C. That's going to be confusing. Sorry about that. So you're going to say, where did that C come from? And then she has two B's. So this is line AC. Sorry about that. All right, so if line AC is tangent to circle D, then line AC is perpendicular. Remember, the upside down T is perpendicular, which means it makes a right angle. So line AC is perpendicular to segment BD. Okay, so that just means that you're going to have a right angle. Okay, and we'll see that in use in a few minutes. Another theorem that we have is theorem 10.2. In a plane, if a line is perpendicular to a radius of a circle at its endpoint on the circle, then the line is tangent to the circle. So we're going to have kind of the same diagram here, so we can reuse that. So if line AC is perpendicular to segment BD, which is our radius, we have a tangent perpendicular to the radius, but we don't know it's the tangent. So all that you have is a line perpendicular to a radius, then we know it's the tangent. So then AC is tangent to circle D. So these are the converse of one another. We talked extensively earlier this year about converse statements, how you have an if-then, and then you can reverse the hypothesis and conclusion, and that's pretty much what's happening here. So I'm going to give you a little example, and I'm going to give you a circle. I'm going to give you a radius, so here's your center, and I'm going to come down here, and I'm going to make this a right angle. So that is a right angle. My radius is 6. I'm going to be looking for X, and then I'm going to be told that this part here is 7. And that's important because it matters where the bracket is. I could have given you the bracket for the whole thing, and it wouldn't be 7. It'd be a little bit different than that. But we're going to be asked to find X. All right, so you have a right triangle, and guess what you're going to use? Drum roll, please. We're going to use the Pythagorean theorem. Okay, so across your right angle is always your hypotenuse. But currently, you are not given the length of the hypotenuse. You are given part of the hypotenuse. If this piece here is 6, all radii, we say it R-A-D-I-I, so that's plural for radius. All radii are congruent. And this little piece here is also 6. So both radii are 6, and you would have to add the 6 to the 7. So here the hypotenuse equals 13. And that's kind of the tricky part here. This 6 is a radius or the leg, and then we're looking for the long leg of this problem. So we would end up with our equation x squared plus 6 squared equals 13 squared. And then you would go through and solve. So we're going to say x squared plus 6 squared is 36. And then 13 squared is 169. Okay, and now I have x squared plus 36 equals 169. So I'm going to subtract 36 from each side. I'm going to get x squared equals 133. So this is not a perfect square, so I'm going to take the square root of each side. I'm going to get x equals 11.5. Okay, and that would be the length of the long leg of this right triangle. And this is part of the tangent. It's not the tangent because the tangent is a line. So this is just a piece of the tangent. So it's just part of a line. Any segment can be part of a line. All right, what we're going to do now is we are going to go to the second page of our lovely packet here. And I want to talk through, I'm going to ask you to do 1 through 8, or maybe we'll do that in a Google Meet session. But I do want to talk through a little bit of vocabulary before we do our last theorem and our last couple of examples. So I'd like to talk to you about some intersection work. So I'm just going to add this into the middle of page 2. So intersections. I'm going to write kind of small here. I'm also going to cover up this part here. So I'm just, after examples 1 through 8, if you printed this out, and I'm just going to kind of squeeze this in. All right, so for intersections, you could have no points, no point of intersection. And there are 2 diagrams that you could have. You could have a circle, like a bigger circle, and a little circle. They don't meet. So there's no point of intersection. You could have something called concentric circles, and they look like that. This is called concentric circles. Okay, so that is no point of intersection. We could have 1 point of intersection. 1 point of intersection. All right, and then that can look like a couple of things. It can look like this, where you have a circle, and then another circle here, and then the tangent would touch in one spot. If you want, you can put a little point in there. It could be like a snow, to me it looks like a snowman, where you have a circle and then another circle, so a smaller snowman, and then your tangent going through once. Okay, I'm really going to try to squeeze here. You could have 2 points, and I'm just going to leave it as 2 points. And then to me, this is a really popular marriage symbol or prom symbol, where it's the intersection of 2 rings. It's really popular, and you would have a point here and a point here where the 2 circles are touching. So we're looking at 2 circles intersecting. Here, they don't intersect at all. Here, they intersect in 1 point. Here, the 2 circles intersect at like just on each other, so it's kind of like that. And then here, it's overlapping circles, and you're getting overlapping circles, so you're getting the 2 points top and bottom. The last thing I wanted to show you before we go to our last theorem are common tangents. Okay, and common tangents can do kind of one of 2 things. So I'm going to call this case A. And in case A, we're going to have a bigger circle here and a little circle there. And it's almost like an X. And I am going to use a ruler here because I don't trust myself. So I'm going to come over here and I'm going to draw 1 as an X, the first part of the X. And then I'm going to do this one over here as the second part of the X. And so these are touching twice. So this tangent is touching here and here. this tangent is touching here and here. So they're common to two circles. I lost my handy dandy ruler, fell. All right, and then you could have case B. So I'm going to sneak case B in here. So case B would be similar. So you have a bigger circle and a smaller circle. And I'm going to grab that ruler. And what we're going to do is go like this on the outside. So those are common tangents. And if it's not big enough, I'm just going to kind of fudge it. All right, and then same thing here. These are common tangents. So it's common because it's touching two circles in one spot. Okay? All right, so this is the last theorem for this week, and it says if two segments from the same exterior point are tangent to the circle, then they are congruent. So we're going to draw basically, it kind of looks like a common tangent, but we're only going to have one circle. So I'm going to have circle D. It's a pretty good circle there. So I have circle D, and I'm going to draw with my ruler, and you can freehand it. It doesn't have to be perfect, but I'm just trying to make this look pretty good at least. So it's a tangent. It's touching here, and it's going through. So I'm going to call this point of tangency A. And now I'm going to draw another tangent over here. Okay, and I'm going to call this point of tangency C, and where they meet is B. And all this is saying is if two segments from the same exterior point are tangent to the circle. So here's our exterior point. So point B is our exterior point, and these are segments. So you actually don't need to look at the line. We're just looking at those pieces of the tangent, so those segments on the tangent. What we now know is that segment AB is congruent to segment BC. Okay, which means the lengths are equal. So the length of AB equals the length of BC. So what I thought would be the most helpful is if we went over to examples 9 and 10 over here. So I'm on the third page of your packet. And we're just going to do these last two examples for this week. So in exercises 9 through 11, I'm just going to do 9 and 10. Line AB and line AD are tangent to circle C. Find the value of X. So they're not showing the entire line, they're just showing the segment. So they're showing part of the line. But these are tangents because they're only touching the circle on one spot. If you have a common point exterior to the circle, which we have here in both 9 and 10, I almost feel like it looks like a clown head or a dunce cap. If you don't know what a dunce cap is, you can look it up and Google it, search it up. But these are saying that these are congruent and those are congruent. So if you kind of have that clown hat, then the pieces, the segments are equal to one another. So we're going to say x squared minus 1 equals 24. And we're also going to say 2x plus 8 equals 4x. You're looking for that common thread. Go ahead and pause the video if you'd like and solve. Okay, so then you would add 1. For the first equation, you're going to get x squared equals 25. The inverse of squaring is square root. Now, technically, you should be getting plus or minus 5, so you should get the positive and the negative. And in this case, they both work, because if you plug in a negative, you would get a positive here. So both the positive and the negative solutions work in number 9. In number 10, the variable is on each side. This is linear. In example 9, it was quadratic because you had an x squared. So I'm going to subtract the 2x. We're going to get 8 equals 2x. And then we're going to divide each side by 2. And therefore, x equals 4. And then you could plug it back in for both of them to see if it works. If I plug in 4, I get 16. 2 times 4 is 8 plus 8 is 16, so I get 16 equals 16, so therefore it works. A lot of the time we can ignore the negative value that our solution would give in geometry because we're looking at a length, but in this case, the x is squared, so that's different. All right, hope this helps.